Welcome back to my Commodore 64 Memories videos. This is where I look at old Commodore 64 software and some of the technical details behind them. Today we have Enigma Force, published in 1986 by Beyond. The developer was Denton Designs, coder Dave Colclough. I hope I've got your name right, Dave. Graphics by Karen Davis and title screen by Karen Davis. Musician Fred Gray. I'm looking at this game because this message asked for mouse support. We're going to have a little technical look at how this game uses sprite stacking to render its game screen. And you can see here that the sprites, as I move the targeting cursor up and down, the sprites are all at the same X position. It's just that the same sprite definitions are reused just vertically, so the vertical positions of the sprites are updated, and the sprite pointers are also changed as the targeting cursor moves down the screen, showing where the raster updates are for the sprite pointers. So you can see the stack of vertical stack of sprites, in this full screen debug view here in C64 Debug GUI. The red bounding boxes, as always, show where the sprites are. We can also see that the targeting cursor in the panel down at the bottom there is also showing a red bounding box, and that means that the targeting cursor is also a sprite. There's a stack of sprites on the left-hand side of the screen, and it's not really being used at the moment, and that's because there's the 4-player characters. And then we have two kind of like explosion objects in Sprite 0 and Sprite 7. And then we have two unused sprites, which will probably get used as enemies come on the screen. So when enemies come on the screen, there we go, we can see that the sprite stacks actually get quite busy. So we've got a lot of detail and graphics being updated dynamically into the sprites as things move around the screen. But these raster interrupts here are very carefully timed. I can see some large amounts of no-ops there which spread out the code so that the code updates the sprite pointers specifically at the right cycles in the raster line to avoid kind of like unwanted visual artifacts. So the Commodore 64 has a schedule of things it does across the whole raster line, which is actually a lot wider than just the visible screen. You've got all of the time left in the border. So apart from the bad lines, which I've gone through before in previous videos, where the VIC chip stuns or pauses or freezes the CPU to fetch extra memory for character definitions, there's also specific cycles on the raster line where the VIC chip will fetch data for active sprites that are active on a particular raster line. So as I move the targeting cursor left and right, you'll see sometimes the disassembly view on the left doesn't update, and that's because the CPU has been paused by the VIC chip interrupting the CPU. But as I move the targeting cursor to the right, you can see, look, these stores into D003, 05, 07, 09, B, and D are all updates into the sprite Y position registers. Then we have some register set up for A, X, and Y. And we've got a set carry and a BCS. Now the set carry and the BCS is basically jumping into that stack of no-ops there up above, and then after the no-ops are finished, it's doing store X, AX, and Y into 63, F9, FA, FB, FC, FD. These are the sprite memory pointers, that basically what tells the VIC chip what frame of sprite graphics memory to display for your currently rendered sprites. So this update here is very carefully timed by the looks of it. And those no-ops are there to help with the timing of the code to precisely time up to a wobble factor of about 2 cycles, of course, because a no-op is 2 cycles. Up to a wobble factor of 2 cycles, or an accuracy of 2 cycles, this code will execute and precisely time its updates. So there's a little bit of self-modifying code which updates how far that BCS instruction branches into the no-op stack there. You can see the self-modifying code being done at 9F18 there, where it's doing a store A of 9F23. 9F23 is the length, or the offset rather, of the BCS, the branch on carry set opcode there. And by changing the position in memory where it jumps into those no-ops, it changes how long the code takes before it does these cycle accurate updates of the sprite frame pointers. It's not a coincidence that sprite frame pointers are being updated in the middle of the raster line. That's where the VIC chip doesn't get, or doesn't fetch the sprite data pointers for its next raster line rendering. It actually does that nearer the right-hand border and the left-hand border. So by precisely timing the update so that you're updating, or the code is updating, these sprite pointers in the middle of the raster line, you're helping to avoid unwanted artifacts or corruption of the sprite graphics as the VIC chip runs down the screen from top to bottom, left to right on each raster scan line. Quite interesting piece of code, actually. I think other games could have made use of this precisely timed technique. I feel Double Dragon, for example, the PAL version of Double Dragon had, I think it was Double Dragon, wasn't it? The player sprites and everything had that kind of like ugly gap between the top and bottom of the player. I think this game technique for rendering tall stacks of sprites would have benefited other games like Double Dragon and stuff like that. If we look at the memory debug view for the graphics map there, sprite data, especially in ICU64, we can see what looks like a whole bunch of compressed sprite frames in memory there. If we change the memory range so that we're looking at sprites in the second VIC bank now, we can quite clearly see a whole bunch of sprite frames being used in the actively displayed video bank for the player characters. So if I control that kind of like robot, the egg-shaped robot thing, right? If I move it up and down, you can see that the vertical movement of this sprite stack is actually reflected in dynamically updating the sprites, and also the sprite data is being dynamically updated for the rotation or the animation of the object, or the player object rather. So you can quite clearly see how the different sprite stacks are updated in memory. It's quite interesting to note that even when the player characters were not on the screen, their sprite data seemed to be dynamically updated, which is intriguing. I think there's 2 copies as well for each game object that uses the vertical stack of sprites there. So while one is being displayed, the other one is being cleared and rendered to. That's why you can see them continuously flicker on and off, I think, in this graphics map debug view there with the sprite data. So to be able to add mouse code to this already hacked and packed and cracked version of the game that I managed to find, we need to first of all extract the uncompressed data and then modify the uncompressed data and code to add some mouse routines. I'm going to be supporting a 1351 mouse, which is the analog Commodore mouse, as opposed to the Commodore mouse, I think, which emulates the joystick. We're not going to do that one because that would be silly, right? I mean, we want to have proper analog mouse support. So we'll be adding some code to do that. So we need to extract these 2 files. One of them is a picture file, which displays a loading picture, and then one of them is the game file, which is already compressed. You can see that it's doing a lot of decompression. There's a whole bunch of decompression code there. The decompression is very obvious because as it scans through the memory there, it's copying bits from all over the place. So that kind of indicates that there's quite a lot of compression already. So we want the uncompressed data. So we need to find where that uncompressed data is. So we'll put a breakpoint in the main part of memory because we saw that the decompression code was executing from the lower couple of pages of memory, right? So we'll just put a breakpoint there, first of all, at the jump, right? And then as it's running the decompression code, we'll then see if we can deduce where the main entry point is. This looks like probably some kind of LZ related compression technique. It's doing a JSR into somewhere to get the next bit code or byte or whatever. It looks quite comprehensive, doesn't it? But anyway, that range breakpoint should trigger as the decompression finishes and then jumps into the game. That's great. It's probably done. Yeah, it's going into the kernel interrupt handler there at FF48. Yeah, and there's not really anything too useful on the stack. I mean, there is the return address for the interrupt code. So it looks like before it starts actually the game code, it's allowing the kernel interrupt to come along and start executing again, which is a real pain. We have to find the code that was executing just before the interrupts were enabled again. So we can either backtrace it through the stack, or we can just hop out and over and through all of the kernel interrupt code, and then we get back to the main game start. There we go. That's starting at 4000. We can verify that by using the CHIS CPU history command in the Vice monitor debug window there. And we can see, there we go. So yes, it's just entering. Let's just make that window slightly bigger. CPU history again. Just wait for it to scroll. We should see, there we go. Decompression code does a CLI and then a jump to 4000. So there we go. I think that's our main game entry point. So we'll save out that whole block of data as a great big uncompressed block of data. We'll save that out to a file on the hard drive, and then we can load it back in again, and then we can start trying to patch or trying to locate good entry points for the mouse routines, and then we can write some patch code for that. So don't forget, when saving out memory, whole memory ranges, we want to bank RAM first, and then save out to a meaningful file name that tells us the entry point is at 4000 in hex. And we want to start saving from, I think we'll just save all the way from, well, we can start saving from 800 to FFFF, I think, because the rest of the memory doesn't look like it was decompressed to, right? I mean, the Commodore 64 basic V2 message is still there. So I think we can save out quite safely that memory range. The first thing that the game code does is that it copies code or data from 4400 to 400. So I think that we can ignore the earlier memory range and just save out that memory range to begin with. So we need to have a look at what loads from DC00. DC00 is the keyboard and also one of the joystick ports that you read as the memory location. It's part of the I/O space on the Commodore 64. Ah, yeah, look. And also, this routine looks like it's setting up what to read, yeah, and then because it was storing into DC02, and then it reads some bits from DC00, which is the joystick, and then returns that. So the routine at A13B there looks like it's reading joystick bits. It also looks like it might have been trying to do some initial keyboard reads as well, perhaps. But yeah, basically AB is returned from this. AB is a 0-page memory location, and that stores the joystick bits. So it returns the joystick bits in the accumulator, and then it stores it into AB. Now, this routine here seems to be decoding if 2 bits are set. Let's just double check something in the standard include library that I have with my source code. So there we go. Those first 2 bits are joystick up and down. So it looks like it's checking for them to be set. So this routine looked like it was reading the joystick bits from the hardware and then inverting the bits. So normally, if you press up on the joystick or down on the joystick, it will show a 0 bit for whichever direction you're pressing on the joystick. Whereas this, it's checking for the inverted of that, so it's checking for a 1 bit. So it looks like it's checking for up and down. My initial thoughts when I look at this code is that it's checking for up and down. If up and down are not set, it looks like it's decrementing F468 memory location and then resetting it to 10. So it looks like there's some kind of like pointer acceleration code here to make the pointer move faster if you're already holding down the joystick in a particular direction, either up or down, or this looks like it's checking specifically for up or down as well. So yes, I think perhaps, yeah, I think there's some joystick, I think there's some kind of like acceleration there of the pointer. So if you center the joystick vertically, then it looks like it's cancelling the vertical velocity. And then if you move the joystick up or down, it looks like it's taking the value at F4DF, subtracting F4D5, was that? Yeah, okay, and then storing it back again, comparing it with the range. Yeah, this looks like it's updating the pointer position up, down, left, and well, up and down. And then it's doing an add here. So we've found what looks like the up routine and the down routine. Then it's doing a load. Oh, then it's doing a test for left and right bits, because that's the next 2 bits. So the first 2 bits are 1 and 2 in hex, or decimal rather, and in hex. But then the next 2 bits are left and right. So that's 1, 2, 4, and 8 values. So yes, okay. So this is code which tests up, down, left, and right, applying kind of like an acceleration value by the looks of it. So the reason why we need to understand where the joystick bits are read and what this code does is that I have a feeling that, as is usual in games, you have different routines for different parts of the game. So there's a pointer controlled part of the game, but you can also take direct control over your characters by moving the joystick around, and then you can control the characters directly, like a mind control mode. So we need to find out, we need to understand what this routine is doing, because if we want to add mouse support, analog mouse support, to the pointer with the panel that scrolls left and right portion of the game, then we need to understand the routine. We need to understand what memory locations this routine is storing to or updating for the pointer position, or when you're pressing fire and stuff like that. So I think looking at this routine here, I kind of understand in broad, high-level terms what this routine is doing. We have up, down, left, and right decoding for joystick bits. We have the acceleration. We have the moving or updating of the pointer X and Y position updates. We also have this code here at A10E, which does seem to be taking the horizontal position and multiplying it by 2 with the ASLA instruction there, and then setting or clearing, and then depending on the carry, it sets or clears a 1-bit at F4EE. So and it's doing an AND with FE to either clear that bit or set that bit with load A and then OR there. So it seems to be doing a most significant bit check. It's basically converting the 8-bit value for X position into a 9-bit value for X position, ready for the sprite to start displaying at those positions. These are not the sprite registers. It looks like it's some temporary working area, because of course the sprites are being multiplexed. So we have to do all of these calculations outside of the realm of or range of the bit chip registers for the sprite. So yeah, that's the fire button bit check as well, which also sets a little flag in a specific memory location. We need to kind of like know these memory locations as well, so that we can set the appropriate data in the appropriate memory locations for X and Y position, and also whether or not fire is pressed. So we need to understand this routine here. Now I've understood the code for a potential code to patch out, I'm looking for some empty memory which is untouched by the game. So this memory range here at 340, up an extended 0 page, it doesn't look like the game is updating it. It looks like it contains 0 values, which are the original values from when the Commodore 64 was powered on, practically. If I go to mind control mode and then exit out of mind control mode and then do other stuff as well in the game, that ranged watch store point doesn't seem to be triggering. So I think that the game, at least with this very high level check, doesn't seem to be using that memory range. So I think we can use this memory range for adding in our own hook code. So the last thing I need to check as well is that where DC02 is updated. So DC02 is the I/O port for the joystick and keyboard data direction register. So we need to make sure that because the data direction register is used or partially used when you're updating which paddle or in this case mouse you want to read for your analog inputs, right? You basically use part of this register when you store values to the upper 2 bits for selecting which paddle or mouse you want to read from. So we need to make sure that the code is not corrupting the mouse that you want to read from for the analog data inputs. Those analog data inputs actually come through into the SID chip, so you have to actually read from the SID chip. But the SID chip can select which analog inputs you want to read for your X and Y values for the device that's plugged into your control ports. So yes, it just looks like that code there was updating DC02. So we need to take a note of that. We need to patch out that as well and make sure that it doesn't update the wrong bits, so that we basically read a consistent mouse device from a consistent control port. After deducing which parts of the game code do what, then we get to be able to write the code. So I wrote the code to intercept the mouse, the data direction register updates as well. So I intercepted those at 340, and then the mouse reads were injected into code, well, have code injections at 350. There is actually quite a lot of code which sets up the data direction register, sets up the correct mouse device that you want to read from. Then it reads the X and Y analog inputs from the SID chip, basically, and then does some acceleration, accumulation, range checking, and position clamping and stuff like that. And there we go. This code then includes all of the game code and then does the relevant patches into the game code to make it call the mouse code. I'll be adding links to all of this code into my GitHub source code repository, and I'll put the link in the description below, so you can have a look at the code and assemble it yourself. But yeah, basically it's now running the mouse code. There we go. So I'm able to move the player characters around with my mouse control now. The BICE emulator emulates the 1351 mouse quite successfully. So I've configured the code so that it reads the mouse from port 1, and then it allows the joystick to still be connected into port 2. So when you go into mind control mode, the joystick will be used to control the character, your player character, with mind control mode. To assemble the patch code and also do all the patching and compressing, just run the Enigma Force.bat file that runs the Acme assembler with the source file. It then runs my LZMPI compression tool. You can actually see that the compressed game now is 31641 bytes long, which is actually pretty good. It's a nice small game file now. Now we have a nice small compressed game file with mouse support. We can just add a picture to it as well and compress that all into one file. So there's a little bit of code, and I'll also include a link to this in the video description below. There's a bit of code which reads in all of the data for the bitmap loading screen. So the bitmap loading screen data is actually extracted from the second file which is on that disk, which is just the picture. Right, so a bitmap screen, a multicolor bitmap screen, needs the screen data, which is one bank of color data, the real color data, which goes into color RAM, and then it uses the bitmap data, which is the bitmap data for all of the graphics that you see on the screen, right? But then it needs the colorization data as well, which is effectively 2 screens worth of data. This code sets up all of the VIC memory pointers for the code. It then copies the second bank of color data into the color RAM specifically, so it copies that from where it was loaded. Right, so that's what the original picture display does. It copies it from 5800, 5900 into D800, D900, which is inside color RAM. Right, so all I did was save out those portions of data to separate files. I also include some initialization code which makes sure that the machine is initialized into a stable state just after decompressing all of this data. And then it does the similar color RAM copy, but the 2 color screens plus the bitmap data are all at the last bank now, right? So this code does different memory setup for the VIC chip to display that data, the bitmap data, from the last bank, the VIC bank in memory. Then the already compressed game data sits in the correct place in memory at 801 in hex. And then all this code then does is that it waits for the last scan line and then initializes the screen. And then the code tests for fire being pressed on both joystick ports. And if fire is pressed on one of the joystick ports, then it waits for the scan line, turns off the screen, and then jumps to 2061. That jump to 2061 just jumps into the compressed game code, which is already sitting at its correct place in memory at 801 in hex, and 2061 there is the basic start command address, right? It's a sys 2061 normally if you run it normally, but if you just include it in memory and then all compress it up together again, then you have a one file of the loading picture which gets displayed and then just runs the game compressed single file as well. So it's put 2 files worth of data into one. And that was pretty easy to do because the compressed file was smaller than the bitmap data as well needed to display the loading screen. So there we go, that worked quite well, quite successfully. So all of this will go into my GitHub. I think we'll leave that video there. I've covered everything I wanted to cover. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Take care, have a great day, evening or night, wherever you are.